Hi, this is the last video in the series devoted to continued fractions, and in this video I want to illustrate what I said about applications of continued fractions with some examples. What you see on the screen is a calculator. The application I was speaking about is basically application to real life. For me, real life is mathematical research. So this is an application to I will show you this application as an application to mathematical research. I will try just to illustrate what I said in the previous recording. So it is frequently the case that some calculation produce as the outcome something close to an integer. And we can suspect that this is indeed an integer and try to explain the phenomenon. Here is a textbook example for that. Let us calculate the following. This is exponent e to the power pi, number pi, times square root of 163. Have a look. What we produced looks very, very close. It is very, very close to this integer. You see how many zeros after decimal point have we acquired. As I said to you, in this case, this trace is misleading. This number, exponent of pi times square root of 163, is not really an integer. However, as I said, this is a textbook example, and even this closedness to an integer, which we see here, requires an explanation. The explanation now is well known. For the sake of this example, I'll just show you that if we simply increase the precision, the situation changes. You see, after so many ninths, we have many digits, and that hence that probably this number is not an integer. It is just very close to this integer. However, in order to guess that something, a result of a calculation, is an integer, this is indeed a reasonable approach. We see that there are many zeros after decimal point or many ninths after the decimal point. We suspect that the result was really an integer. Sometimes, however, and more frequently in fact, the outcome of a calculation is not an integer but merely a rational number. Again, not all, but many computer calculations are constrained with certain precision. And we may not have the exact result just an approximation to the exact result. Here is an example. We take a rational number. This is certainly a rational number, an integer divided by an integer. And we corrupt this rational number a little bit by 10 to the negative 15. Now, the outcome is very close to a rational number, but it is still a rational number. In fact, this rational number slightly corrupted. Here is the outcome. From this outcome, if it is not made up but comes as a result of some calculation, we cannot guess, just looking at that the number was rational. With rational numbers, we don't have this hint with so many zeros or nines after decimal point. You may say that we still have something periodicity of the decimal expansion, but with that size of denominator, six-digit number, you will not observe the periodicity easily. The way to go is to use continued fractions, which will really help. So let us call this number somehow, say x, and let us look at continued fraction representation of this number. The software I am using implemented the algorithm I showed you, how to take a number and produce a continued fraction representation of this number. In this case, this number is slightly bigger than 1. Here is the continued fraction representation. There is a slight difference in notation. One, we put at this point, we put a semicolon. The software put a comma instead. Other than that, that is the same thing. So you think about semicolon at this point after 1. Other than that, this is continued fraction representation of what we produced here of this number. Let me highlight it, of this number. Now, let us just look at this representation. Some sequence of integers as expected, positive integers after the first one, clearly, all positive integers. And we just see an irregularity. This integer is way bigger than all the others. This irregularity actually tells us about a very good approximation, a very good rational approximation to the number we started with, to our x, this number. So what we can do, we can try to cut it right before this irregularity. Let us do that. Namely, we want to calculate Pn and Qn in our notation for finite continued fraction cut at this point. That is possible in this software. That will evaluate Pn and Qn, two pairs of them, two convergence, for this cut-off continued fraction. Here you go. The best guess made from this calculation for our number x is this one. Sorry. Which is exactly the number we had corrupted. This way, if this number was not made up, as in this case, but came as a result of some imprecise calculation, we have a very good guess about the rational number we started with. This is the number. That is how this works. You may say that this example is made up. Let us look at yet another example, which we already know something about. This line of code calculates the value of Riemann zeta function at 12. If you look back at the additional text about Riemann zeta function in our syllabus, you will find that the value zeta of 12 is rational, some simple factor times Bernoulli number, up to a power of pi to the 12. So we suspect, actually in this case we expect, we know that, but in some cases, when you do research, you don't know that in advance, that divided by pi to the 12, this number is rational. What the number is, this is value of Riemann's zeta function at 12. I took first 10,000 terms of the series 1 over n to the 12. That's 1 plus 1 over 2 to the 12 plus 1 over 3 to the 12 plus so further up to 10,000. Should be pretty precise. And I divided this sum by pi, the number pi, 3.1415, so further, taken to the power 12. I know that if the sum was taken to the infinity, that is a rational number, something we know precisely what is that. The sum is, I cannot take the sum up to infinity. This is only a calculator. So I can take the sum up to a big number, 10,000 in this case. We calculate the sum, and now what I want to do, I want to guess, to make a guess about this rational number. We know it is rational, I want to guess it back. How do I do that? Same thing. I first of all, if I want just this to look at the number, 10 to the minus 6, so you have several zeros in front of this one. And after that, a sequence of digits, you hardly can guess that this sequence of digits represents a rational number. The precision is quite high, 100-digit precision, 100 significant digits, but still you don't see any signs of rationality. A number slightly bigger than 1. You can tell nothing better about that. Let us see what happens when we take this number and expand it into a continued fraction expansion. Something big, and here you see something huge. This absolutely obvious irregularity allows me to guess that this is indeed a rational number. And the number should be, I again call it z, the number should be I again calculate the convergence, the last convergence, up to this point. I cut it here right before the irregularity. So I take this one, 691 over this denominator. So my guess is going to be that the number is this one. Is this guess correct or not? So again, look, I took something which looks as complete garbage. From decimal expansion, I can tell nothing. From continued fraction expansions, I can tell something. I want to stress, nothing I'm telling you here is a proof. But it is not, the appearance of this huge number is not a proof that what we are dealing with is really this rational. However, it is a clue. In research, you first may need a clue. After that, you find at least a direction to think about the subject. So, in fact, in this case, the clue is correct. If we multiply this number by something, so I took 699 over this denominator, and I multiply by factorial, divide by power of 2. Why do I do exactly that? You can look up in the additional text about Riemann zeta function. A classical theorem of Euler tells us that if you take the value of the sum of this series divided by pi over 12, pi to the power 12, pi to the power 12, up to exactly this factor, you will produce Bernoulli number. That is what we produced. Now we can check what is the corresponding Bernoulli number. That's the 12th Bernoulli number. And the sign difference is also easily explained in the text about Riemann-Zeta function in the theorem proved by Euler. You see that indeed our guess about what rational number it should be, this rational number, is absolutely correct. We produced back Bernoulli number out of that 12th Bernoulli number. That is how continued fractions can be used in mathematics research. I'm sure this kind of application is possible in other fields of activity as well. I simply don't know about that. So I wanted to illustrate, and I hope I succeeded to illustrate the power of this method without proofs, but just how to guess with the help of continued fractions, how to make educated guesses. That is all I wanted to tell you about continued fractions, and thank you for listening. Stay safe